Okay. Good afternoon, everyone. My name is Tong. Today I'm going to present my master thesis, Evaluation of Mobile WiMAX Performance in a Metropolitan Vehicle Application. My thesis advisor is Professor Marco Brutusser. So why is Mobile WiMAX Performance is so important in vehicle application? As we know, with the development of future intelligent transport system, more and more networked vehicle applications are designed and developed to address different kinds of transportation problems, like on-road safety and the transport efficiency. For example, the lane change warning system will give the driver a notice when they try to change the lane in case of the potential traffic accident. Also, the parking assistance system will provide the driver the parking availability information so that they can quickly find the nearest parking slots. So in these vehicle applications, large number of data are collected and stored locally, and then needs to be transferred or disseminated to other vehicle nodes or roadside infrastructures. So in vehicle network, Mobile WiMAX is one of the most popular technologies because of its high throughput, large coverage, and mobility support. Especially in metropolitan environment, it has its own advantages. So let's return to the question why the performance is so important. Before WiMAX deployments are used by vehicle networks, the performance of typical vehicle applications of WiMAX needs to be evaluated. So also propagation characteristics of WiMAX, especially related to application performance. For example, the impact of intermittent connectivity on data transfer over WiMAX needs to be evaluated. So after that, this evaluation result will guide us for the future planning and design. So in my master thesis, I implement a WiMAX-based network vehicle application called ParkNet in a real metropolitan environment. After measure a large number of WiMAX status, we analyze the propagation characters and prediction model. So the main primary questions to be answered is the first one: what is the propagation characters of Mobile WiMAX in a metropolitan environment? Second one: what is the prediction model of that? And the third one, when we implement WiMAX in ParkNet, what is performance of data dissemination in such application? Currently, there are a large number of researchers working on Mobile WiMAX. So on this slide, there are some results coming from Europe. So in Norway, we find that in urban area, the WiMAX coverage can reach 1 kilometers, but for the suburban area, because there's less constructions between transmitters and the receivers, so the coverage can reach 2 kilometers. And the similar result come from Italy. And we can see that the coverage is up to 996 meters. Also, some experiments from Asian countries like Korea, that some researchers put more than 5,000 portable PC on the buses to test the TCP performance. They found that the dynamic TCP throughput can reach 1.9 Mbps, and the average round trip time is 164 milliseconds. For the uplink, under outdoor environment, the throughput can reach 1 Mbps, but for the indoor it's only 300 kilobps. Also, they use some path loss model to predict the WiMAX performance. So path loss model is a radio propagation model that predicts the path loss under a certain environment. So in free space, the path loss exponent is 2, but for the non-light outside environment in urban area, it can reach 3.6. This result is from Croatia. And in UK, the similar result very similar result. The path loss exponent is 3.1. But for the suburban area, we can find that the path loss exponent is lower than that in urban area. In Norway, it's only 2.6, but in some suburban area, there are more constructions, so the path loss exponent can still higher than 3. In Italy, the result is 3.03.
So what was specific about these environments that led to, for example, in Croatia, having such a high path loss exponent?
That depends on the construction distributed and density of construction in such environment.
But in particular, tell me about Croatia. Why? I mean, I can also construct an environment that would actually have a path loss exponent less than 2.
Yeah.
All right, by creating a constructive mode of interference. So what was special about Croatia?
It's randomly selected the environment. It's like the building is it's normally like 10 meters, and the density is just like the normal urban environment. So there's no special character of this environment.
I would guess that for Croatia it must have somehow been a more densely packed urban environment in order to have such a high path loss exponent.
Yeah, I think because I remember the dense of the building is high. That's one point. And another thing is because they put the WiMAX base station on a low building, so it is embraced by other tall buildings. So because of this, the path loss exponent is higher than that from other countries. Sorry. Yeah, go on. Okay, so we implement ParkNet application in our experiment. The ParkNet is a parking assistance system. So the basic objective of that is to detect the roadside parking availability and provide such information to the users. The basic idea is to use the mobility to solve this problem. So we put an ultrasonic sensor on the passenger side of the vehicle. This ultrasonic sensor is connected to the onboard PC, and it detects it measures the distance between the first obstacles on the roadside and itself. At the same time, the onboard PC will give the time step, and GPS device will provide the coordinates information. So after processing this data by using a machine learning algorithm, or we can call it a parking detecting algorithm, we can get the parking statistic information. So in our system, the sensor we used is waterproof ultrasonic sensor, and the data rate is 20 samples per second. For the GPS, we use Garmin 5 Hz GPS. That means 5 samples per second. So after synchronize this data, the coming data type is kernel time, sensor reading, and corresponding GPS coordination. So this is the centralized structure of ParkNet system. So as we can see, these sensing cars collect large number of data, and after that, this data will be centralized through wireless channel, and then transferred to a remote server. So on the server side, the parking detecting algorithm will keep running and process this coming data and visualize the result to the end user. So why we use ParkNet in our experiment? So as we can see, firstly, it's a typical network vehicle application. The second one, because parking problem is one of the big traffic problem in metropolitan environment, so it is very suitable in such environment. And also, as we can see, currently we use a centralized network structure. So the basic communications between the vehicle and the roadside infrastructure. So it is very suitable for our objective and motivation. So ParkNet system has its own requirement for the data dissemination. As we can see from this figure, so the traffic, there's a comparison between different applications and ParkNet. So the traffic monitoring system will collect the real-time traffic information and disseminate this information to the users. But because the traffic changes a lot during the time, so it is very sensitive to the time. But for the ParkNet, because the roadside parking availability doesn't change so frequently, so we don't need such real-time systems for the data uploading. So in other words, it's a delay-tolerant data uploading system. In this way, we don't need these vehicles under the coverage all the time, so it will save the cost for the base station. However, on the other hand, we need an efficient data transfer mechanism to guarantee that all the collected data could be transferred during the coverage. So in ParkNet, currently we use a micro element file uploading mechanism. So in this mechanism, the basic idea is we split the large file into small pieces. As we know, when you transfer a large file, because of the intermittent connectivity of the wireless network, so or when the connectivity is down, so the file transfer will be aborted. So after we split the large file into the small pieces, it will save the time caused by the file transfer abortion. So in our system, we use SCP operation to transfer the files. After split these files into 20 kilobytes, we add the sequence number for each one. And at the same time, we transfer the earlier collected data. So that means if you collected this data earlier, it will be transferred earlier. So the advantage of that is on the server side, this data could be processed earlier. This is the basic workflow of our uploading mechanism. So as we can see, if the network is down, so it will abort the file transfer. But because the file size is very, very low, so it will not waste too much time.
So is this a stop and go protocol, or is this a stop and go?
Yeah, actually there are two threads. One thread is keep detecting the connectivity and feedback the result, and another one is keep trying to use SCP to transfer the file. So if the connectivity is up, the SCP will build a TCP connection and transfer the files. But if it is not, it will just keep detecting result. Okay, so we implement ParkNet in the Brooklyn area in New York City. We select the 8 experiment vehicles and running on the 10 routes in Brooklyn area. So this is basic routes figure. So as we can see, this greenhouse is the base station, and we use different colors to represent different routes in our experiment. So these routes, some of the routes are very close to the base station, but for others, they're kind of far away from them. So for this route, sometimes it is not under the coverage, but sometimes it is. But for these small loops, almost all the time it is on the coverage. So we make the experiment more general. The total experiment time, the entire experiment time is more than 6 hours, 6.5 hours. and the total distance is more than 50 kilometers.
So who was involved in this experiment? Who was involved in the experiment? You mean cars?
Yes, some of the WiMAX students and some students are from Brooklyn Polytechnic University.
So were you using the WiMAX that Brooklyn Poly has, or?
Yeah, the base station is started on their building.
Okay.
But the PC is from our lab.
No, I know. The WiMAX is also from your building. Keep it to them. So.
Yeah, for sure. On this road, the speed limit is from 25 miles per hour to 35. So the basic system deployment is the same as ParkNet system. However, we add the WiMAX status monitoring system. We use the OMRF framework to collect the WiMAX status and receive the signal strength. So both ParkNet availability information and the WiMAX status are collected and transferred through WiMAX to the remote server, and then split into different kind of server for future usage. So as we can see, the WiMAX base station is located on the 16-meter buildings in Brooklyn area, that is in Polytechnic University. So the direction of antenna is faced to the north and faced to the south. Sorry, and the beam width is 120 degrees. And the base station is the NEC WiMAX base station, which is operated at 2.59 gigahertz, designed for end-to-end server deliveries. So we configure the transport power to 32 dBm, and the antenna gain to the antenna direction is 22 dBi. On the client side, we use the Samsung NC10 notebook. It is with the Intel WiMAX link adapter. So this adapter the data rate of this adapter can support 13 Mbps for downlink and 3 Mbps for uplink. So as I said before, we use the OMRF framework to monitor the WiMAX status and the signal strength. So OMRF framework is a flexible software framework for measurements collection. So the basic components in our experiment is OMRF client, OMRF proxy server, and OMRF server. The former two parts are located on the vehicle, and the OMRF server is located on the remote face. So similar to the micro element file uploading system, there are still two threads running on the OMRF framework. The one thread is to keep detecting the connectivity and the return feedback. And for the WiMAX client, it will collect the measurements all the time and start locally in the proxy server. So when the connectivity is up, the proxy server will try to connect to the remote server and uploading the measurements. But if the connectivity is down, it will keep the loop and just waiting for the connectivity results. So the basic measurements we collected includes the download link RSSI, and with the time step and the coordinates. And also the GPS will provide the speed, vehicle speed, and we got WiMAX status. The data rate is 1 sample per second. Also, we got the time step for each file, each parking availability files. So after that, we analyze these measurements to get the propagation characteristics, including the coverage, connection, and RSSI distribution. So on the left side, that is the RSSI value over the distance. So as we can see, the x-axis is the distance to the base station, and y-axis is the RSSI value. So with the increase of the distance, RSSI value decrease. The range of the RSS value is between -40 to -98. So if the signal strength is lower than -98, we cannot detect any result. The maximum distance is only 519 meters because of dense constructions on high buildings nearby the base station. We also can see that there are some outliers in the red rectangles. So to analyze these outliers, we project these measurements on the Google map, as we can see on the right side. We use different colors to represent different RSSI values, and also we find that these outlines are placed on this location. This triangle represents the WiMAX base station. So as we can see, between this area and the base station, there's a few buildings. There's a plaza and there's a road between them. But for the same distance, we can see, for example, this point, this location. Between the base station and this location, there are many constructions between them. So mostly these measurements are under non-line of sight condition. But for this area, it's on the line of sight condition. So that is why these measurements are higher than those with the same distance. Because of the still limited on these experimental routes, and because of there are many traffic constructions there, so the mean speed is only 1.67 meter per second, and the mean connection is 402.6 seconds. But as we can see, the minimum connection time is half a minute. So next, we want to get the prediction model from this large number of measurements. So we aim to getting a path loss model of the form. Path loss equals A plus B times log 10 D over D0 plus XG. So A is the reference path loss value, and D0 equals to the reference distance is 1 meter. And D is the distance from the transmitter to the receiver. So B is 10 times path loss exponent, and the XG is a normal random variable with 0 mean. So the most important variable is this N and the XG. We want to plot these two numbers.
What does XG stand for? What is XG?
XG is prediction error for this model.
Why might you have prediction error?
Why?
Why might you have prediction error?
Because after we fit the model on the measurements, but for each measurement and the prediction error, there's some gap between them. So for each measurement, it's not just a phase error, because we just fit the line for this measurement. It's not exactly the same as this measurement. So that is why the XG take place. Okay. I can give you the analysis later on the later slide. So we use actually we use the least square regression analysis to analyze this result. So this figure is the RSSI over the log distance. So after we use MATLAB to fit the line on these measurements, we can get the coefficient from the formula, like A and B.
Did you remove the outlier data?
Yes, I moved that. Because it doesn't match the trend of the distribution. So we move the outliers.
So how did you choose that one and not the stuff at 1.4? You see at the x-axis 1.4?
Yes.
That's also outlier. So what made you decide to extract something as outlier versus something else not as outlier?
So actually, you may see from this one, right? So I used two. The first one is because this one is like out of this trend, and the second one is because we projected all these measurements on the
map.
On the map, yes, from the coordinates, we can find some of them are definitely line of sight on line of sight conditions. So it will the measurement will be unknown. So because of these locations, I make a filter to filter all of these kind of measurements.
In the end, you did it by hand. Right.
It's kind of by hand.
So why not make that box go, the red box go down one more?
This one?
Yeah.
Go down.
A little bit more. Or why make the box that big? Why not make it that big or this big?
Because as we can see, this measurement is far away from the trend of the distribution, right?
So you're not getting my point. My point is if you made it just a little bit higher, you can make exactly the same sentence. So what made your cutoff region be exactly that cutoff region, not...
Oh, this one is just to show you that this is an outlier. It's not the exactly field to create.
Okay.
It's just to show this is outlier.
Yeah, all right.
So after that, we can get the formula for RSSI. So because RSI equals to the transmit power and times, plus transmit antenna gain and receiver antenna gain minus pass loss. So from the formula 2 and 3, we can get the final result for the pass loss. And as we can see from the formula for the pass loss, exponent is 3.008. And then we analyze the error, prediction error. So the prediction error is RSSI measured minus the RSSI predicted. So basically that is, for example, for this D, that should be this distance. So we still use a statistical analysis approach to analyze it. And after we run it in MATLAB, we can get the fitting plot. And the MATLAB will show the final result of different variables. So the result is it fit the normal distribution for zero mean and the variance is 57.1. So in summary, that is the basic path loss model for our experiment.
What is 57.1 tell you?
It's variance. The variance.
All right. Well, right. That's not what I meant. I meant physically, what does the 57.1 tell you?
That is okay. That is this error square this error. Okay. That's the difference between the prediction and the real measurement, and then square this value.
Okay.
So finally, let's look at the data transfer performance. So we plot the number of RSSI over the such RSSI value, and also we use the blue one to plot the number of transfer files under such value. So totally we transferred 608 files, and this RSS value is from minus 40 to minus 79 dBm. So we plotted also on the coordinates. So the red points means all the measurement, RSSI measurement, and the black ones represent the area where the file is successfully transferred. So as we can see, the maximum distance to support the file transfer can reach 396 meters. And for the data transfer performance, the average duration is 251.9 seconds, and the minute duration is just 7 seconds. So because this will happen, so we care about data rate. So in 25 times data dissemination, the average data rate is approximately 70 kilobps. It's only 0.435 per second. As we can see, it's very low. So we are very interested why this happened. So for this reason, we did a comparison experiment. So in this comparison experiment, firstly we used one SCP operation to transfer one large file, and then as we can see, that is blue curve. And then we split this large file into n small files. Each of file is 20 kilobytes. That is the red curve. And for the black one, we just use the same mechanism in our implementation. As we can see, the throughput doesn't change all the time. It's still 70 kilobps. So this happens because the dynamic behavior of TCP. So it will take some amount of time to reach the maximum sending rate to the maximum bandwidth. So because the file is very small, so before the TCP can reach the maximum bandwidth, the file transfer is already completed. So what we want to achieve in our experiment is we want to get a fast reaching the maximum throughput, and the throughput is very high, but the transfer time it should be very small. However, with when the size of files increases, the max data rate increases too. But at the same time, the transfer time is also increased. That means the risk of file transfer abortion increased too. So to solve this problem, we propose some trade-off between the data rate transfer and risk of transfer abortion. We want to use some mechanism to make sure the throughput can reach the maximum or reach a very high level, and after that, these files could be transferred one by one. So we propose some solution for the future. The first one is we need a proper dynamic file size, so that even if we use TCP, it can still reach a higher throughput. And also we can modify the TCP protocol itself. The third one is we can replace TCP by using UDP and move the reliable mechanism on the up layer. So that is a basic result from our experiment. So in summary, we implement a WiMAX-based vehicle application ParkNet in a real metropolitan environment. We got the mobile WiMAX physical performance, like the coverages can reach 590 meters, and connection time for the WiMAX is 402 seconds. The RSS ranges from minus 40 dBm to minus 98. Also, we got the path loss model for our condition. So the path loss experiment is 3.008, and the error can fit the 0 min and the 57.1 virus. Finally, we got the file transfer performance. So the basic duration, the average duration of file transfer is 251.9 seconds. But we have to say that the minimum duration is only 7 seconds. So that means the intermittent connectivity happens in our experiment. Also, the file transfer rate is only 70 kilobps because of the small file size. So after the analyze, we need to upload and modify the mechanism for the future use. Any questions?